we have seen what evaluation graphs look like for neural nets. These evaluation graphs, these are this type of visualizations that we have seen and that we see all over deep learning literature. It's things like that. I'll be there in a second. Things like this that express the order of calculations and the dependency of every intermediate result on the previous results. So these guys are called evaluation graphs. We have seen that once we have an evaluation graph, we can run backpropagation through it to efficiently calculate all the derivatives of one scalar result with respect to any number of inputs. Now, any calculation necessarily defines a graph. In order to calculate anything from given some inputs, some parameters, you always do something with these inputs, then do something with a result, then do something with a result to finally give you a final result, right? There is no other choice. So a computer program will always work this way. So any evaluation will necessarily define a calculation graph. So it means that every evaluation defines a sequence of feed-forward operations similarly to a neural net. I have a chapter in the book, chapter 9, that actually shows you some toy code that helps you concretely build evaluation graph in memory with operator loading in C++. But conceptually, any evaluation defines a calculation graph. Now, what is adjoint differentiation? That's backpropagation over these evaluation graphs. And it's not limited to neural nets. It's actually applicable to any evaluation. And what it does is propagate adjoints backwards in the reverse order through a given evaluation graph. And we have seen that it offers constant time efficiency, which means you get all differentials for the expense, for an expense similar to one evaluation of a final result, as long as your calculation is scalar, which means that the final result, the output layer, as we call it in deep learning, is a real number. So an evaluation graph in a compact form, we could say that you start with a vector of inputs, you do something with it, you get an intermediate vector, let's call it A1, you do something else with it, you get another intermediate vector, A2, and so on and so forth. So you apply a sequence of vector-to-vector functions, which here I call J, to finally obtain a final result, which I call A of L in the final layer. And in order to calculate all the derivatives of the final result with respect to the initial inputs, all I have to do, as we have seen, is to backpropagate this sequence of calculation, to carry it in the reverse order, to perform the sequence of adjoint operations in the reverse order to backpropagate derivatives. And we have seen that the backpropagation equation is simply that the adjoint of AL, the derivative of the final result to itself, is obviously 1. So we know the last one. And by the channel, once we know the adjoint of AL plus 1, well, we can find the adjoint of the previous layer AL by this adjoint equation where AL is the Jacobian, the derivative of AL plus 1 with respect to AL, so that will be the Jacobian of GL, of the ELF function, times the adjoint of AL plus 1, right? Now here, in this notation, these steps G, so that will be G1, here G2, G3, etc. For avoidance of doubt, these are, in this case, what I call building blocks of calculation. We will see, I will define them more specifically. So these are like elementary steps of calculation for which we know how to calculate them and we know how to differentiate them. These are not activations. We're no longer talking about deep learning here. Okay? So it's best that I give you an example to clarify all this. So very simple example so that it can hold on only one slide. Let's take Black-Scholes, okay? For once with non-zero interest rate and dividend yield. So, well, we all know Black-Scholes' formula, right? It's this one, where df is the discount factor to maturity, f is the forward, so it's got this form. We calculate the standard deviation, sigma square root of t, the log moneyness, d, log of f over k divided by STD, so how far I am from the money in terms of standard deviations. Then need to calculate d1 and d2, so that's d plus half a standard deviation and d minus half a standard deviation, which gives us n of d2 and n of d1 and n of d2, the probability to end in the money, respectively under the spot measure and the risk neutral measure. And finally, the call price will be the discounted FP1 minus KP2. Okay, it's Black-Scholes' formula. And here I just translating these steps into an evaluation graph. So in order to apply backpropagation, I need to split my calculation into a number of layers where every layer only is a known function of a previous layer. So, for instance, I know that I have my input layer, which are the 6 parameters to my Black-Scholes function, but I know that, for instance, the strike, I will need to use it in the final layer so that I can calculate discount factor times FP1 minus strike P2. So what do I do? Normally, I would have to, on the last layer, to pick the strike on the input layer, but then my calculation would not be neatly arranged in layers, and I couldn't apply backpropagation easily. But it doesn't matter. All I have to do is to copy over the strike when I need it. So that just gives me a dependency, which is the identity, and there's an arrow missing here. I'm sorry for that. Oh no, it's not missing. It's from the strike. It's fine. So this edge here is just the identity function. So on the first layer, I compute the discount factor and the forward. That's from S0, R, Y, and T. And I also, and the standard deviation as a function of sigma and t. And I carry over the strike because I will need it for further layers. So the discount factor, I have it, but I will just apply it in the final layer. So I will carry it over layer from layer to layer. Same thing for the forward. Now, from knowing the standard deviation, the forward, and the strike, I can calculate my D. Once I have my D, I can calculate D1 and D2, which gives me P1 and P2, which altogether gives me my call price. So here I just splitted my implementation of Black-Scholes into 5 layers, where each layer is a known and rather trivial function of the previous layers. So how do I go from the input layer to the first hidden layer? Well, I apply a vector to vector function G1. And what is G1? Well, it's this thing. If you look at the first element of the first hidden layer is the discount factor. That's exponential of minus R times T. So that's how it goes. Okay? Then I have the second element, that's the forward, that's the spot times exponential of R minus YT. That goes like that. The third one is the standard deviation, that's sigma square root of T. So that's expressed here. And the last one is just identity applied to the strike to carry it over. So the last element X yeah. The fourth element of A1 is the fifth element of A0, so it's just X5, etc., etc. Similarly, I have G2, the function that I apply to go from the first to the second layer, G3, G4, and G5, right? And you can see that these functions are all trivial, right? They're like building block functions. So what's the point of doing that? Because I could have done it in only one layer. I could have said that my call price is the Black-Scholes function applied to these 6 guys. And then I have it all in only one layer. So what's the point? The point is that I get is that all my layer-to-layer functions, if I split it, if I split my calculation into small enough pieces, all these calculations become trivial. And in the end, this is something that not a lot of people realize. But when you code a calculation of whatever complexity, when you code a complicated model to calculate your counterparty credit risk, when you simulate a lot of different market variables far in the future, etc., etc., in the end of the day, you're just assembling a small number of elementary building blocks. At the end of the day, it's all about multiplications, additions, divisions, subtractions, square roots, logarithms, exponentials, maybe 20-something building blocks, yeah? Maybe you have some sine, some cosine, some hyperbolic sine and cosine in your calculation, up to 20 building blocks, no more than that. And whatever calculation, numerical calculation, can be split in maybe a long sequence of these 20-something building blocks. And what is very nice about this is that these building blocks, not only we know how to calculate them, but we know how to differentiate them. And there is a very small number of them. So we can tabulate them once and for all. We know that the derivatives of a log is 1 over x, that the derivative of a square root is 1 over 2 square roots, that the derivatives of the sum, the derivative of the left-hand side term is the right-hand side term, that the derivative of the right-hand side right term is the left term, and so on and so forth. We know that once and for all. So we can like produce once and for all a table of for these 20-something derivatives of these 20-something operations, right? So that we can conduct automatic backpropagation of any calculation we want. So that's why I've been splitting Black-Scholes into 5 layers, and actually I should have splitted it further. I just wanted it to hold on one slide. Because, for instance, here you see I have log of x2 divided by x4, then again divided by x3. This is not an elementary building block. This is the composition of 3 elementary building blocks. First, I divide x2 by x4, then I apply logarithm, then I divide the result by x3. So this is not one building block. You and I, we're human beings, we know how to differentiate this, of course. But the machine knows only how to differentiate building blocks. So we would need to split it more. But I just wanted to illustrate how it works. Because once we split our calculation neatly in layers that each depend only on the previous one in a trivial way, well, we can run backpropagation over this calculation to get all the derivatives of the final result with respect to all the inputs. So we have, as in deep nets, for any calculation, we have a feed-forward equation that defines the evaluation graph. Again, we start with the inputs, and we move from layer AL-1 to layer L by applying a known vector-to-vector function, GL, right? Until we get a final result, Y, which is just the final layer, a capital L. So in Black-Scholes, the steps we have are our calculation defines all these intermediate steps, all these function GL. So in Black-Scholes, we have G1 here, G2, G3, G4, G5. So once we have the feed-forward equations that correspond to represent our calculation, we also have the backpropagation equations directly. So for any calculation where we want to compute the differentials of a result to the input, so we want dy over dx, which is dal over da0. Once we have split this calculation into these elementary pieces j, for which we know the Jacobians, which with a slight abuse of notations, I call gl prime. These are vector-to-vector functions, gl. So gl prime is really a Jacobian matrix of dal over dal minus 1. And these guys are known, right? For instance, in Black-Scholes, this is my Jacobian of G1. So it's the Jacobian matrix of layer 1 to layer 0. This is the Jacobian matrix of G2, G3, G4, G5. And you can see that they're all pretty trivial because these are my G functions, and these ones are just the differentials of them. So note that the Jacobian of the output layer, G5 prime, that's a vector, and it has to be because the calculation produces a final result, which is a scalar, which is a real number. So the last calculation, the output space, the output dimension of the last calculation has to be 1. Necessarily. So its Jacobian will be a vector. Once we have done that, we can run the backpropagation algorithm over this calculation graph. We have identified the calculation graph with all its steps G, and we know the Jacobians G prime. We run it once and store all the intermediate results A, just like we saw for neural networks. And then we can compute all the derivatives in constant time by backprop, by running the adjoint equation. So first of all, the adjoint of a final result of a final layer, AL bar, well, that's DAL, that's the differential of AL to itself, so it's 1. So we initialize it to 1, but it's called seeding. Then we have the main backprop equation, right? Since this backprop equation here, which is an elementary application of a chain rule again, the adjoint of AL, when we know the adjoint of AL plus 1, we can find the adjoint of AL by left multiplication by the Jacobian matrix of GL plus 1. Why is that? It's because by definition, the adjoint of AL is the final result of a DAL. That's the definition of the adjoint. Now, by the chain rule, I can split that into DAL plus 1 over DAL, and that's the Jacobian of AL plus 1 to AL, times DA capital L over DAL plus 1, and that's by definition the adjoint of AL plus 1. So it means that I know the adjoint of the last of the output layer, and I have a recursive relationship between that gives me the adjoint of any layer as a function of the adjoint of the next layer. So I can run it backwards to find the adjoints of all the layers, and finally the adjoint of A0, which are by definition the derivatives of the final results to the inputs. So that's what I want. So first I have a seeding step where I have an initial condition for my adjoint equation, which is the sensitivity of the final result to itself is 1. It's rather trivial. Then I have a backpropagation equation, which is an application of a chain rule that gives me the adjoint of any layer as a function of the next layer and a known Jacobian. And finally, I can pick my results just by saying that the sensitivity of a final result to every element in the input layer is the adjoint of that element by definition. So, of course, it's not super interesting in Black-Scholes, where we have only 6 inputs, only 6 derivatives to calculate, have delta, vega, rho, etc. And it's really not worth applying AD. But what is very nice is that these exact same set of equations apply in all cases. So they apply with large evaluations taking 6,000 inputs too. And it's very, very interesting then. Because you go through the same chain of operations that defines your calculation, and you go through every node only once to apply the adjoint equation in the reverse order, which means that you will get all your derivatives for a cost similar to one evaluation of a function. Now, what I'm leaving as an exercise to you, but I really recommend you do differentials of them. So note that the Jacobian of the output layer, G5 prime, that's a vector. And it has to be because the calculation produces a final result, which is a scalar, which is a real number. So the last calculation, the output space, the output dimension of the last calculation has to be 1, necessarily. So its Jacobian will be a vector. Once we have done that, we can run the backpropagation algorithm over this calculation graph. We have identified the calculation graph with all its steps G, and we know the Jacobians G prime. We run it once and store all the intermediate results A, just like we saw for neural networks. And then we can compute all the derivatives in constant time by backprop, by running the adjoint equation. So first of all, the adjoint of a final result of a final layer, AL bar, well, that's DAL, that's the differential of AL to itself, so it's 1. So we initialize it to 1, but it's called seeding. Then we have the main backprop equation, right? Since this backprop equation here, which is an elementary application of a chain rule again, the adjoint of AL, when we know the adjoint of AL plus 1, we can find the adjoint of AL by left multiplication by the Jacobian matrix of GL plus 1. Why is that? It's because by definition, the adjoint of AL is D, the final result of a DAL. That's the definition of the adjoint. Now, by the chain rule, I can split that into DAL plus 1 over DAL, and that's the Jacobian of AL plus 1 to AL, times DA capital L over DAL plus 1, and that's by definition the adjoint of AL plus 1. So it means that I know the adjoint of the last of the output layer, and I have a recursive relationship between that gives me the adjoint of any layer as a function of the adjoint of the next layer. So I can run it backwards to find the adjoints of all the layers, and finally the adjoint of A0, which are by definition the derivatives of the final results to the inputs. So that's what I want. So first I have a seeding step where I have an initial condition for my adjoint equation, which is the sensitivity of the final result to itself is 1. It's rather trivial. Then I have a backpropagation equation, which is an application of a chain rule that gives me the adjoint of any layer as a function of the next layer and a known Jacobian. And finally, I can pick my results just by saying that the sensitivity of a final result to every element in the input layer is the adjoint of that element by definition. So, of course, it's not super interesting in Black-Scholes, where we have only 6 inputs, only 6 derivatives to calculate, have delta, vega, rho, etc. And it's really not worth applying AD. But what is very nice is that these exact same set of equations apply in all cases. So they apply with large evaluations taking 6,000 inputs too. And it's very, very interesting then. because you go through the same chain of operations that defines your calculation, and you go through every node only once to apply the adjoint equation in the reverse order, which means that you will get all your derivatives for a cost similar to one evaluation of a function. Now, what I'm leaving as an exercise to you, but I really recommend you do it if you want to understand this stuff, is just show that if you apply this equation, if you apply this backpropagation equations to Black-Scholes, so to these functions g and there's Jacobians g prime, that you effectively find the well-known Black-Scholes Greeks, right? And you will, unless I made some mistakes here, which I never checked. So hopefully there are no mistakes in my Jacobians, in which case you will have to find the Black-Scholes Greeks. Please let me know if you don't. So, about these atomic building blocks, what we just did, we split a calculation from inputs to a final result, which in this case was Black-Scholes. We split it into a sequence of simpler calculations, where every layer only depends on the previous one. Why did we do that? Well, so that we can apply backpropagation to compute derivatives over this sequence. So once we have the sequence of operations that defines our calculation, we can run the corresponding adjoint equations in the reverse order in order to get all the derivatives. If we push this logic to the limit, what we can do is to split any calculation in a sequence of so-called atomic building blocks. Really, the atomic building blocks of any mathematical calculation, which are additions, differences, multiplications, division, power, exponential, log, square root, sine, cosine, etc. And we have a very limited number of these building blocks. Again, about 20. And yes, I know that's maybe a mind-twisting realization, but any numerical calculation is always potentially a very long sequence, but a sequence all the same of these 20-something building blocks. Nothing more, nothing less. I always have questions when I present this stuff. People in the audience tell me, yeah, but if I implement a Bessel function, then don't I need to tell the machine what is the derivative of a Bessel function? No, you don't implement a Bessel function. You implement a sequence of operations that you mean to approximate the result of a Bessel function. But we don't care about what you mean. We don't differentiate what you mean. We differentiate what you do, right? And what you do is always a sequence of elementary calculations. And this is what is getting differentiated. Yeah?
What's if there is a condition in the sequence?
Yeah, that's the next slide. Oh. And that's a problem. So there's actually a nice article by my friend Rolf Paulsen in Wilmot. So you know that I'm not supposed to do that, but Wilmot is an expensive magazine, and I really like this paper, so I stored it so that you can access it on my website. He called it, "This is not Sparta," because 300 Greeks will not stop us. So I really recommend it. It's non-technical, but it's funny, and it shows quite well what's mind-twisting about AAD. And in particular, he insists on the fact that, well, yes, any calculation is a sequence of a limited number of building blocks. And for this 20-something building block, obviously we know their derivatives. We know that derivative of exponential is exponential, derivative of log is 1 over x, derivative of square root is 1 over 2 square roots. We know that, and we can tell that to the machine once and for all. We have only 20 derivatives to write, okay? Therefore, yeah, we can code them once and for all, and then we can completely automate backprop. We can, once we know the sequence of all the j's, and since we know all the Jacobians, all the j primes, then we can automate all this calculation. And this is what gives us AAD. Okay? So you had a question about control flow. Control flow is, is somewhat painful, not only for AAD, but for any kind of differentiation algorithm. It doesn't work much better with, say, finite differences. The problem of control flow is that it makes your function discontinuous, and the discontinuous function is not differentiable. So yeah, there's this code by Rolf, say, somewhat vertiginous realization that any calculation, like the Monte Carlo estimate of a counterparty credit risk value adjustment on a netting set of thousands of exotic transactions, is still a sequence of elementary operations. A very, very long sequence, but a sequence all the same. Yeah? So this being said, these mathematical equations are more mathematical equations when you do maths, right? Then you deal with more than sequences of building blocks, because in maths you also have limits, differentials, integrals, these kind of things. But once it becomes numerical, once you put it on a computer, there's no more limit, there's no more theoretical differential, there's no more theoretical integral, just a sequence of operations. There's and again, it's not about what you mean to do, it's about what you effectively do. And what you effectively do is a sequence of operations and control flow, also called branching in computer science, that are the if this then that statements, right? You also have the loops, but the loops, it's okay, they're enrolled into sequences of statements. You have while loops, which are combinations of while loops and if statements, so our problem is really the if statement. So for instance, if x is more than 100, return 1, otherwise return 0, that gives you a digital, right? So obviously, this guy is not differentiable. If you try to differentiate it with finite differences, you may be in a situation where before bump you're here, and after a small bump you're here. So what you're going to get by finite differences, if you try to apply it to a function with control flow like that, you will get something utterly unstable. And that's actually well known. And you can do the test. You can try to differentiate a digital. You will not like the result. Now, with AD, AD doesn't apply any bumps. AD is an analytic differentiation. So conceptually, it applies an infinitesimal bump. So which means that you will always be on the same side on the control flow, before and after, right? Which means that in the case of a digital, the differential that AD will give you will always be 0. AD always differentiates on one given side of a control flow. It always differentiates over the branch where the calculation was executed. But it doesn't differentiate through control flow. Bumping tries to differentiate through control flow and fails. AD never differentiates at all through control flow. But my point here is that no differentiation algorithm is able to differentiate through control flow. And there's a good reason for that. It's because it's impossible. You can't differentiate a discontinuous function. So what can you do about that? Well, you can't work on the differentiation algorithm, you have to work on the function itself. So you have to approximate this function by a closed one that is continuous. And that's called smoothing. And options traders, they always do that systematically. They would never book a digital as a digital. They would book it as a tight call spread. Because then it's a continuous approximation to your digital, so like the blue line here, and then everything's fine. Before bump you're here, after bump you're here, your differential is well defined, right? So now, if you are interested in smoothing, I have one of my favorite presentations on SlideShare about fuzzy logic, where I really love this one because I start with, on capital markets, we have been doing that for decades for digitals and barriers. But in this presentation, I remind all these things, and I show that this is all just a particular application of fuzzy logic. And once you realize that, you have a completely general smoothing algorithm that you can apply to any kind of product. So if you're interested in smoothing, I would definitely encourage you to read this one. In conclusion, all calculations define a graph down to 20-something atomic building block J's. Like deep nets, all evaluation graphs may be arranged in successive layers, each an elementary function G of a previous one. And since this function J are elementary building blocks, the Jacobians are well known. Once the evaluation graph and its steps G are known, along with the Jacobians G prime, and the graph was run once so that the intermediary results A, L were stored, then all the derivatives, the final result of the D inputs, can be computed in constant time by the backprop equation. So if we can automatically produce a graph from a code, we're done, right? Once we have a graph, an evaluation graph, all we have to do is to run this adjoint equation. We seed it on the final layer, and we get, we can recursively calculate the adjoint of a previous layer, knowing the adjoint of the next layer. So we're pretty much done, but we still need, given a piece of code, to figure automatically an evaluation graph. Now this bit, we don't know yet how to do that. Because the evaluation graph for Black-Scholes, I didn't produce it automatically. Obviously, I produced it by hand. I just wanted to show you that for any kind of calculation, it is possible to produce an evaluation graph like this. Once we have this evaluation graph, then we can run AD, or which is the same as backprop. We know this already. We have seen it at least twice today. We know the adjoint of a last layer, and knowing the adjoint of the next layer, we can calculate the adjoint of the previous layer. And the adjoint is by definition the sensitivity. The adjoint of something is the sensitivity of the final result to this something. So the adjoint of the input layers gives us exactly the derivatives we want, right? And this backpropagation equation traverses the evaluation graph, stopping on each level exactly, on each layer exactly once, therefore giving us all the derivatives for a similar computational cost to the forward evaluation of a graph, because you will be going through the same sequence of operations, only in the reverse order. Okay?